Oh, okay, so today we have Jaume Tarrús from Indiana University. So Jaume did his PhD in Barcelona, and then he has been working in Munich, in Barcelona Autonomous University, and now in Indiana. And he's an expert in effective field theories and Qualconium exotics. And he's going to tell us about exotic Quarkonia in effective field theory. So the room is yours. So.
Okay, thank you, Miguel. Thank you for the nice introduction. So, as you said, I'm going to talk about exotic Quarkonia in effective field theory. So first, let me introduce standard Qualconium. So these are bound states of a heavy quark and an anti-quark. And the first of this kind of state, which was discovered, was the IGFAE, which was discovered almost at the same time at Brookhaven and Slack in 1974. And this was identified as a charm and touch charm. And seeing in this figure, you can see, well, there's a figure from one of the original publications. You can see this peak corresponding to the mass of the IGFAE around 3.1 GeV. Then a few years later, the upsilon was discovered, which is the analog state in the bottom and anti-bottom sector. And again, here, one of the figures from the original publication, where this peak here corresponds to the mass of the upsilon 1s. These are around 9.5 GeV. So Quarkonia was realized very early on that they were non-relativistic bound states. And this means that they can be organized in terms of a principal and an angular quantum number. So in this way, they are sort of the QC analog of the hydrogen atom. Then the spectrum can be obtained from the Schrodinger equation using some suitable potential. So the question was, what was the potential that one should use? And the first attempts were to compute this potential in perturbation theory. And this led to a Coulombic potential coming from the one-gluon exchange. However, the spectrum was found not to be corresponding to a Coulombic potential. So this leads to several developments where people try to find a phenomenological expression for the potential. And I think the most popular one is the Cornell potential, which has a Coulombic term, a linear term, and a constant. And then in parallel, there was work in finding an unperturbative expression for the potential. And this was found as the Wilson loop, static Wilson loop, which can then be evaluated with non-perturbative techniques such as lattice, which are the results that I'm showing you in these two figures. Here, data from obtained from the lattice for the potential. And in red, there is a fit of the Cornell potential to this data. And you can see that indeed, the Cornell potential reproduces or parameterizes the lattice data very well, both in short and long distances. So this here is the separation between the quark anti-quark, and this is the energy axis. Then the second figure is looking at shorter distances. So here, this range here corresponds roughly to this part here of the other figure. And again, the red dots is lattice data. And here you can see it compared to a perturbative computation of the potential. And you see that for short distances, the perturbative computation does actually describe well the potential. Okay, so the final step was to connect the Schrodinger picture to QCD. And this can be done with effective field theories. And here the idea is that if one has a system with multiple well-separated scales, instead of just computing the fundamental theory and then expanding in the small ratios of these scales, one can implement expansion at the Lagrangian level, and then one has effective field theory, which one can use to compute all low energy processes. And this has several advantages, in particular that since only the relevant interactions and degrees of freedom at low energy appear, this makes the computations easier. Also, we only have to deal with one scale at a time, which also simplifies computations. And well, finally note that one can build effective field theory even when the fundamental theory is not known, or we don't know how to compute in a particular energy region of interest, as would be the case for QCD at low energies. So in the case of Qualconium, as I said, it's a non-relativistic bounded state. This means that it's characterized by these three scales: the hard, soft, and ultra soft. So in this case, the hard scale is the heavy quark mass. The soft scale is the relative momentum, which can be written as the heavy quark mass times the relative velocity. And these scales as the inverse of the distance between the heavy quarks. Then the ultra soft scale is the scale of the binding energy between the heavy quark and anti-quark. And these scales of the heavy quark mass times the relative velocity. And in addition to this, since we are in a QCD system, we have also the lambda QCD scale. Then by integrating out these scales in sequence, we can build effective field theories. So first, if one integrates out the heavy quark mass, this leads to non-relativistic QCD. However, this is still not the most appropriate EFT to describe the Qualconium bound states, because we still have two dynamical energy scales. So one can go one step further, integrate out the soft scale, the relative momentum, and this leads to this EFT called potential non-relativistic QCD, in which we recover the Schrodinger formulation. And in the EFT, the matching coefficients take the form of the potentials. So there are two versions of potential non-relativistic QCD, depending on how the soft scale scales respect with lambda QCD. So if we take the soft scale or the relative momentum larger than lambda QCD, this is weak coupling. And in this case, this can be integrated out in perturbation theory, and this leads to the Coulombic potential that I showed you before. However, this is only valid for short distances. And then the more general version is the strong coupling regime, in which both the soft scale and the lambda QCD scale are integrated out simultaneously. And this is valid for any distances, but in this case, the potentials are in general non-perturbative objects, and one can only write them as Wilson loops, which then can need to be evaluated also with non-perturbative techniques. So with this picture, one could explain the spectrum of Qualconium states. And here in these two figures, I show you this side, the Charmonium spectrum. Here are the quantum numbers of the different states. These are the scale, the mass scale. And here the same for the Bothomonium, states. So the standard Qualconium states are the ones here labeled by the spectroscopic notation, and these are well described by this this picture that I just been explaining. But this good agreement changed in 2003 with the discovery of the X3872, which did not fit the standard predictions, and this is the state that is found here. And this was followed in the following years, but more discoveries of other states which were either unexpected or that show properties that were different from the ones expected from a standard Qualconium. And these states are found in this region here, close and above this heavy meson pair thresholds. And well, in a way, well, all these states are called exotic Qualconium, and they are usually labeled by X, Ys, and Zs. And well, this would be what I'm going to discuss in the rest of the talk. Okay, so in a way, from the effective field theory perspective, the appearance of these unexpected states in this region of the thresholds, it was not so unexpected, because these are all degrees of freedom in this region, which are integrated out in the construction of potential non-relativistic QCD. And this means that one cannot expect that the theory or the EFT to give accurate results in this region. Okay, so all these exotic states must contain some heavy degrees of freedom, that heavy quarks, quark anti-quark pair, and some light degrees of freedom, and this can be either gluonic or light quarks. And well, there have been many models proposed to explain them. So here you see some of them. So for example, they could be Quarkonium hybrids, so a heavy quark anti-quark with some non-trivial gluonic state, and several tetraquark models depending on how the heavy and light quarks are arranged. And also very popular is that some of these states can be shallow bond states of two heavy meson, of heavy meson pairs. And this would be the case, for example, of any state that is very close to a threshold is very likely to be a heavy meson molecule. And there are also other models, such as this Qualconium proposal, in which you could think of the exotic state as a quarkonium core bound together with some cloud of like quark hadrons, such as baryons and so on. However, there is no coherent comprehensive framework to describe all these exotic states, and in particular, none that is well connected to QCD. So this is one of the major challenges that exist at the moment in understanding the QCD spectrum. So one of the main ideas that I want to explore in this talk is the use of an hierarchical expansion between the heavy and light degrees of freedom to describe these exotic quarkonium states. So here the idea is to work in analogy to the 1.5 approximation for molecules. And in this case, the closest analog to exotic quarkonium would be a diatomic molecule. And there what one does is, when using the 1.5 approximation, is to first assume that, that the heavy quarks are static and look for the energy levels, sorry, the nuclei are static and look for the energy levels of the electrons. So in this figure here, in the sketch of the energy levels, the solid lines would correspond to the energy levels of the electrons. So these now depend on the distance between the nuclei, and the separation between the energy levels of the electrons is of order of m alpha squared, which is the same sort of separation you get in hydrogen atoms. So these are called electronic static energies. And then in the second step, one would find the nuclei bound states on top of these static energies that function as sort of a potential. And these bound states will appear naturally in the minima of these static energies. And because of this, they would be separated by energy gaps, which are much smaller than the typical separation between the electronic static energies.
Sorry,
and
so
yeah.
The upper line represent molecules in atomic physics, or?
Sorry, can you ask again?
Yes. So the upper line represents so the upper part represent molecules.
This?
And yes, on the
no,
lower one.
Both lines represent energy levels of the electrons, and
okay.
Each one of these states would be the final molecular state. So you first look at the electronic energy levels, and then you add the vibrational energy, which would be this, right?
Okay, understand.
So so the electronic energies are obtained with the nuclei static. So this is like the first step in the 1.5 approximation. And then in the second step, one finds the nuclei bound states, right? Which are found supported by the static energies that function like a potential. And because the only place where you can get a bound state is around this minima of the static energies, the separation must be smaller between the vibrational energy levels than between the energy levels of the electrons. And in an effective field theory language, the hierarchical expansion comes from the fact that these two scales are separated. Okay, so we want to apply a similar picture for exotic quarkonium. And in this case, we would have also some static energies corresponding to the light degrees of freedom, so the gluons or light quarks. And this would appear also separated by energy gaps, in this case of order lambda QCD, since the dynamics of these light degrees of freedom is dominated by this lambda QCD scale. And then the final exotic states are the bound states of the heavy quark anti-quark pair on top of the static energies. And these again should be separated by energy gaps, which are smaller than the ones that separate the static energies. And since the binding energy is of the order of the sutras of the scale, this means that the hierarchical expansion in exotic quarkonium should come from the separation between these two scales. So the question, of course, is how one does obtain these static energies for the light degrees of freedom. And well, this can be defined as the energies of the static eigenstates of a quark anti-quark system in the static limit, this in NRQCD. And then to compute those, what one can do is find an operator in NRQCD that has the same quantum numbers as the desired static energy. So it overlaps with it. And then one can look at the last time correlators of these NRQCD operators. And then one can just look at the log, and this would give you the energy of the static eigenstate that overlaps with the NRQCD operator that we have chosen. So with some specific choice of operators, one can write these correlators as a static Wilson loop with insertion of some light degree of freedom operators, which carry the appropriate quantum numbers. So here, the quantum numbers of the static energies are the ones here. So we have the distance between the heavy quarks. We have also the quantum numbers of the light degrees of freedom, in this case, the spin, kappa, parity, p, and also possible charge conjugation, flavor, and so on. So here I will mostly focus on the spin and the parity, which are the ones that we need to, which are more important in order to construct the EFT that I will be discussing. And also more important is that the static energies appear in representations of a cylindrical symmetry group, which is called Bisu infinity H. So when you have a system with a static heavy quark and an anti-quark, the symmetry of the system is not spheric, but cylindrical for rotations around this heavy quark anti-quark axis. And the representations of this cylindrical symmetry group are given by these three quantum numbers. The capital lambda is a rotational quantum number, which is the eigenvalue of this operator here. So the absolute value of the projection of the spin matrix of the light degrees of freedom into the heavy quark axis. So this R hat is a unit vector in the heavy quark anti-quark axis. Then there is an eigenvalue for Cp, which is usually denoted by a G or a U for plus or minus 1, and this is usually written as a sub-index here, and also for lambda equals 0 states. There is also an additional symmetry, which are reflections with respect of a plane that contains the heavy quark axis. And in this case, one writes this eigenvalue as a superscript with a plus or a minus. Okay, so to compute this, so this is a non-perturbative object. So again, one needs to use some non-perturbative techniques, and this has in fact been done in some cases with lattice QCD. And the most well-known results are these for the well-done in Quench lattice and QCD, so they correspond to gluonic operators only. And well, these are these results in this figure from Jukut Morningstar. These are somewhat old results, but there are more recent computations with higher precisions. But what they obtain is essentially the same as these older results. Okay, so this axis here is the distance between the heavy quark and anti-quark pair, and this is the energy axis. And these are the different static energies that one obtains. So the ground state corresponds to the standard Qualconium states, while the excited states correspond, in this case, to the exotic Qualconium states. And you can see here the different labels, the sigma G plus, pi u, and so on. These are the labels of the representations of this infinity H. So here there are two interesting behaviors of the static energies. So we have that in the short distance, they form degenerate multiplets, and this is because in the short distance, so when the distance between the heavy quarks goes to 0, we expect to recover this spherical symmetry. And this is a larger symmetry group, which means that several representations of states that live in several representations here will go to the same representation of O3 times charge conjugation in the short distance limit. In the long distances, all the static energies become linear, and this can be understood as the formation of a flux tube, which can be described with an effective string theory. And then the different energy levels would correspond to different excitations of a quantum string. And in fact, this gives a very good prediction for the separations of these static energies. Of course, this is all done in Quench lattice and QCD. This means that these excitations here correspond to purely gluonic excitations. So the exotic states supported by these static energies would correspond to the hybrid Qualconium picture. But then one could ask what happens when we have dynamical light quarks. And here we don't have a complete picture, but we have some partial information also from lattice determination. So from this paper here, from the SSMTCL collaboration in 2000, they studied the ground state static energy in the first excitation, both in quench and unquenched simulations. And they found here that there is not a significant difference between the two. And we also expect this to happen for the other excited static energies. However, when one has dynamical light quarks, one could also get or write different static states that one cannot obtain just with quench lattice and QCD. And one of these states is the ones corresponding to heavy meson pair thresholds. And there is also these other results, also from the SSMTCL collaboration from 2005, in which they studied the quark anti-quark static energies and the threshold and the first threshold, as well as the mixing between the two. And these are the results that they found. So for short distances between the quark and anti-quark, the quark anti-quark potential is the ground state. But at this energy level, where you cross the energies of corresponding to the masses of the two heavy mesons, so this is prescale, so that the masses of two heavy mesons is the zero. And when you arrive at this energy, then the ground state changes to be the heavy meson threshold. But the quark anti-quark state still survives, but as an excited state. Yeah. So sorry, there is a question?
Yes, is this spring breaking what we are looking at?
So
okay.
This is what is called the stream breaking, the change of the ground state from the quark anti-quark to the heavy meson pairs.
Okay.
So here the idea is that you have a mixing, and due to this mixing, when the quark anti-quark or when the energies cross the mass of the two heavy meson, then it changes from the ground state changes from the quark anti-quark to the heavy meson. But this is because there is a mixing potential between the two. And in fact, so the two states do not actually cross, the physical states do not cross, and the separation between the two is equal to the mixing potential at this distance where they change, right? But you can still think of the system as some quark anti-quark and some quark anti-quark state and heavy meson pair state, but interacting together with a mixing potential, right? And then when you diagonalize the system, you get the physical states, which are the ones shown here. But you can also work on the other basis. Okay.
Okay. Thank you.
So the thing is, when you are far from this crossing, then you can work them as independent states. But when you're close here, the mixing potential is important. This is the issue. And well, you can think that a similar picture would happen when you cross with a threshold with any other of these static energies here. But for now, there is only lattice data for this case. Okay, so this was for isospin 0, which is the sector of Qualconium, but one could also apply the same kind of picture for isospin 1. In this case, this would necessarily include light quark mesons, since you cannot have isospin 1 operators with just gluons. And here there is no available lattice data, but we expect to have this spectrum of static energies formed by these three types of static energies, right? So the ground state would likely be like a static energy, which would be the same as the standard Qualconium 1, but with shifted up by the mass of some of the light quark hadrons that you need to add, so you are in isospin 1, for example. Then you would get also heavy meson thresholds. And you can also imagine that there are some excited states similar to the hybrid static energies, which the heavy quarks in the short distances are not color-octet, so they are repulsive. And then in the long distance, there will be some confining potential coming from the formation of a flux tube. Okay, and what is nice of this picture is that different models that I showed you before, they could be interpreted as different states living on top of these static energies. Then this same picture based on the Arctic expansion can also be, applied to any doubly heavy hadron, such as like doubly heavy baryons, would be like two heavy quarks and a light quark, also doubly heavy tetraquarks. So two heavy quarks and two light quarks. This is in fact a state which has been observed recently in LHCb. This is called the TCC++, but one can also think of more types of states like open heavy flavored pentaquarks or some sort of hybrid heavy baryons and so on. So for the case of doubly heavy, yes? Miguel, there is a question?
There was no question.
Okay, sorry. So for doubly heavy baryons, okay, let me go back here. So one of the issues in computing this sort of static energies by spin one is that these are unstable static energies. So you can always decay strongly from these states to the ground state, which would be quarkonium plus light quark mesons or like baryons or something. So this makes it difficult to compute on the lattice. But for the case of doubly heavy baryons, this cannot decay strongly to lower states. And this makes it possible to make computations for the static energies for these states, even in a, well, obviously with unquenched simulations. So these are the results that I show you in this figure from the Yarram Valley. So the ground state is the one here. This corresponds just to spin 1/2 positive parity light quark operator. So this is just one light quark, but there are also more interesting states. For example, this one here, this green and red, this correspond to different projections of a spin 3/2 with positive parity operator. And again, in the short distance, we recover the O3 symmetry. So these two states are degenerate. And there is also lattice data for these doubly heavy tetraquarks. This from, well, there are several papers. I'm showing you the ones from these people. This is also from 2013, and these are the static energies one finds for, well, anti-quark. Okay, so now I want to go to discuss a bit the work we have done in building an effective field theory to describe these heavy quark anti-quark bound states on top of the static energies. And this is built using these two expansions. So the fact that the heavy quarks are non-relativistic and the radioactive expansion. And in principle, we will not assume any particular scaling between the soft scale and under QCD. So we will integrate them both out at the same time. And so in this way, this EFT is a generalization of a strongly coupled PNR QCD. So we usually will call the EFT Bohr-Oppenheimer EFT because it reproduces this approximation for exactly Qualconium at leading order in the EFT. Okay, so the EFT, Bohr-Oppenheimer EFT, is formulated in terms of these capital psi fields, which are labeled by the quantum numbers of the light degrees of freedom. So the spin, the spin, which is kappa, and the parity. These fields depend on the center of mass coordinate of the heavy quarks and the relative distance also from the heavy quarks, which is the small r. The time, obviously, and then they have spin indices for the light degrees of freedom, which is this alpha. I will always use Greek letters for the spin of the light degrees of freedom, and this I is the spin index for the heavy quarks. Then the Lagrangian is just written like this, as any other non-relativistic EFT in terms of some Hamiltonian, in which one writes the operators giving you the different interactions. So one should sum over all the light degrees of freedom quantum numbers that are relevant for a particular problem. And well, the question is how we obtain the most general set of operators that go into the Hamiltonian at each order in the heavy quark matrix expansion. So here what we need to know is how to build operators in irreducible representations of the cylindrical symmetry group. And what we do here is to find look for some projectors that act onto operators in all three representations and project them into these infinity edge representations. So to do so, what we do is look first at this eigenvalue equation for the projected spin matrix of the light degrees of freedom. And this gives us these eigenvectors, which we call projection vectors. So these are the projection vectors that get you from a basis of the spin in the z direction to a basis of the spin in the r direction, so in the direction of the heavy quark anti-quark axis. And then from these projection vectors, one can define the projection matrices that we are interested, which are defined like this. So you can use this projector and acting onto an operator, which lives in this spin representation kappa, would project it into a representation of this infinity H labeled by lambda, capital lambda. Now, when building the most general set of operators going to the Hamiltonian, we know that, for example, factors of the spin of the heavy quarks or the angular momentum of the heavy quarks, these always carry a suppression on the heavy quark mass expansion. So this means that the number of these objects that one can add to an operator at a given order is finite. However, this is not the case for these spin matrices of the light degrees of freedom. You can add as many of those to any operator at any order. So, of course, you want to build like a scalar operator out of the spin matrices, but we know that the square of the spin matrix is just identity, so this is not a problem. But you can also build another scalar operator, which is this one here, which is the even powers of the r dot s, right? And these are all of these are scalar operators. So this means that you could multiply any operator you can write, you can think of, by one of these powers, and you would get another operator which would be valid for your Hamiltonian at any order. So this seems that you might have an infinite number of operators that you can build like this. However, this is not the case, because if you plug in this decomposition of r dot s on these projection vectors, you can compute all these powers, and this turn out to be always be the sum of this factor lambda 2 to n times some projection matrix. So what is this telling you is that the number of independent powers is equal to the number of projectors, which is finite, right? Because the number of projectors goes from 0 or 1/2 c to the absolute value of kappa. And in fact, what this relation is telling you is that the number of, a basis for a basis for these matrices is precisely the projector matrices. And with this, we know how to compute or how to write the most general set of operators at each order. So another interesting use for this relation is that one can invert it and obtain expressions for these projectors in terms of powers of this r dot s. And this is nice because you can do this without having to specify a representation for the spin matrices. Instead of this other process, which you do need to have, to carry out this explicitly, you need to actually have a representation for the spin matrices so you can obtain then the projection vectors and from this build the projection matrices. Okay, so now we can go look at these operators going to the Hamiltonian. So we expand this into the heavy quark mass. Leading order, you have the static potential. And next to leading order, you get the kinetic terms. This is the kinetic term associated to the relative momentum. So the relative coordinate, this is the one associated to the center of mass. And then you get a 1 over mq suppressed potential. And of course, going to higher orders, one would get more and more suppressed potentials. Okay, the static potential is a scalar in the spin space of the heavy quarks. So can only be decomposed into the spin space of the light degrees of freedom. And as I argued before, the general basis for this decomposition is on the projection matrices. So this is the most general set of operators you can find for the static potential. And then for 1 over mq suppressed potential, you have two pieces, one that depends on the spin or angular momentum of the heavy quarks and one that does not. This one that does not decomposes in the same way as the static potential, while the one that does is given here in its most general form. So here we have factors of the spin of the heavy quarks or the angular momentum of the heavy quarks, and this is contracted with the spin of the light degrees of freedom. So there are here two ways of contracting this because you can also use these r hat vectors. So you can think this as the spin and the tensor spin. couplings. But instead of using these O3 bases, we use additional infinity H bases. So we write these two possible couplings. For the angular momentum of the heavy quarks, this is orthogonal to r hat. So there is only one possible way of contracting this. And then finally, we need to multiply in both sides with the projection matrices to obtain the most general set of operators. And well, this is how we construct this general set of operators depending on the spin or the angular momentum. Okay, so then the next question is how we obtain these potentials. And this is done by matching von Oppenheimer EFT to NRQCD. And here the matching condition is that to the fields of the EFT are matched to this operator in NRQCD. So this operator is a heavy quark in position x1, an anti-quark in a position x2, and then these phi's are Wilson lines that connect the heavy quarks into the center of mass. And in the center of mass, we place an operator depending only on the light degrees of freedom with the appropriate quantum numbers. So then one can, well, this is a normalization, which is in principle unknown. This needs to be determined too, but well, we will not need it for what I want to show at the moment. So one can then compute correlators in both sides in NRQCD and BOEFT in terms of these two states. And by expanding each side in the heavy quark mass, one can identify the potentials in the von Oppenheimer EFT with different contributions in the NRQCD side. So the leading contribution here is just the propagation in time of these static heavy quarks, and this leads to Wilson lines, which would here be represented by these lines here. And when you add the Wilson lines from the definition of the operators, you get these Wilson loops, again with insertion of the slight degree of freedom operators in the center of masses. And this is the same sort of Wilson loop that was giving us the static energies that I showed you before. So what this is telling you is that the static potentials in the EFT match the static energies in NRQCD. This is at leading order, so this is nice. And this can be also extended at next to leading order in the heavy quark mass expansion to obtain the independent and angular momentum dependent operators that I showed you before. So in this case, one needs to add to the propagation of the heavy quarks subleading operators. And for example, for these spin and angular momentum dependent terms, this means you need to add these two operators here. This is the kinetic term for the heavy quarks, and this is the magnetic coupling. So for instance, these, the first of the operators I show you is given by this matching expression here, which is a bit cumbersome, but this basically depends on this correlator here, which corresponds to this Wilson loop, which in addition to the light quark operators that I showed you before, also include now this B field in the temporal side. So this comes from the insertion of, sorry, this term here in the propagation of the heavy quarks. And well, we have also expressions for the other potentials, but this is a bit more involved than this one. And if you are interested, you can find them in the paper. Okay. So now to a specific example. So we know we have lattice data for the gluonic excitations, which correspond to heavy hybrids. And these are generated by these gluonic operators written here. So we have, for example, spin 1, the lowest energy one is this 1 plus minus, corresponding to basically a B field. And two different projections of this corresponds to these two static energies. So the pi u projection is the lambda equal 1 projection, and the sigma u minus is the lambda equals 0 projection. These are generated by these projection matrices here. And well, for the rest of operators, you get these different projections, and these are the ones that generate the other static states that you can see in this figure corresponding to the lattice data that I showed you before. So for spin 2, you have three possible projections, like the sigma. This again is the 0 projection, the pi, the 1 projection, and the delta, which corresponds to lambda equal 2. So these are the projectors that generate those. And okay, so at leading order in the EFT, and here I'm going to just focus on the lowest energy state. So the one generated by this operator here, corresponding to these two static energies. So for this case, at leading order, we get the EFT, we get a Schrodinger equation for the side field. So remember, this is a vector field in the spin indices of the light degrees of freedom. So this has three components, and this then gets these two potentials corresponding to the two static states, multiplying these projection matrices, which are matrices in the spin space of the light degrees of freedom. So what you have here is that the different components are mixed through these potentials in potential matrices. So one can diagonalize the potential matrix and recover the traditional Oppenheimer formulation, and this is done by acting onto these fields with the projection vector. So basically changing from a basis of the spin in the Z direction to a basis on the R direction. And this is what one obtains. So now the potential matrix is diagonal, but the price one is paying is that this kinetic operator now is does not commute with this projection vector. These projection vectors depend on the angles that define the heavy quark axis, and therefore the angular derivatives here can act onto this projection vectors well. This sort of term is called magnetic coupling because it's mixing the different static states. And this is something you can also find in analogy with the atomic molecules. However, here the difference is that this is more important than in the atomic molecules because of this short distance degeneracy between these two static states. Well, also to this mixing, the angular wave functions of these states, which are hybrid states, are not eigenfunctions of the square of the angular momentum of the heavy quarks, but of the sum of the square of the sum of the angular momentum of the heavy quarks plus the spin of the light degrees of freedom. And to denote the eigenvalue of this operator, I will use this calligraphic L to differentiate it with the regular L, which I will use for the eigenvalues of the square of the angular momentum of the heavy quarks. Okay, so obtaining these potentials from the lattice, we can solve this coupled Schrodinger equation and obtain the energy levels for the heavy hybrids. And this is these results that I'm showing you here for the different quantum numbers of the heavy hybrid states. And here in this axis, you can see the masses. And well, you can see that we get plenty of states. Here, the color is coding the static states that contribute to each one of these states. And you can see that they appear in degenerate multiplets corresponding to different spin states. Oh, sorry, the different heavy quark spin states. Because at this point, we are not including corrections depending on the heavy quark spins. Then in black, there are several experimental neutral charmonium states. And you can see that there are several candidates to fit into our predictions here, but there are also some states in between our predictions. So this is all in this column for the 1 - and this is because this is where most of the experimental states are found, because this is the easiest quantum number to generate experimentally. And what this is indicating is that, well, there can be states associated to heavy meson thresholds, which will appear in this region, but also some of these could also be associated to highly excited quarkonium states, for example. We can do the same for bottomonium hybrids, so bottom anti-bottom hybrids. In this case, well, again, similar picture, plenty of states. And in this case, there is only 3 exotic bottomonium states with no charge. And all of them are 1 - and they are these 3 states here. And 2 of them, the 10,753 and the 11,020, these fit nicely with our predictions. While the third one is in between here, and it's very close to a B meson pair threshold. So it's very likely to be a shallow bound state of the 2B mesons. Then I'm going to go back to these 2 later on. So keep those in mind. And the next step would be to introduce the spin-dependent corrections, so the hyperfine corrections to the masses. hybrids coming from the operators that depend on the spin of the heavy quarks that I showed you before. And well, for a gluonic operator with a spin 1, there is some simplifications. So there are only 2 operators instead of the number that one would expect from the formula I would show you before. But well, and then to compute the hyperfine contributions, one can just use standard perturbation theory to compute these corrections. However, here the issue is that these potentials are unknown. They have not been computed on the lattice. So here we need to use some extra approximations. And what we did was to work in the short distance regime. So in the case in which the relative momentum, the soft scale, is smaller than lambda QCD, and this can be integrated out perturbatively. And this is equivalent to doing the multiple expansion. And this is nice, but because then we can work in this theory with the coupled PNR QCD, in which we can factorize the dependence on R from the non-perturbative physics. Okay, so the field of the EFT, this corresponding to the hybrid, would match in weakly coupled PNR QCD to a field for the heavy quarks in an octet state, which is this O here, times the same gluonic operator that defines this field, plus or multiplying also the normalization. Okay, and then what we can do is expand the Wilson loops in terms of diagrams in PNR QCD. These are diagrams in the position space. So the leading order term is just the free propagation of the heavy quarks in an octet state. And this is giving us this contribution to the potential, which is the octet potential, computed in perturbation theory. And from the propagation in time of the gluonic state, one gets some constant accounting for this non-perturbative correlator here. And this is called the glue lamp mass. But then one could have subleading diagrams, which include multipolar interaction between the heavy quarks. For example, this is a dipolar interaction in which the 2 heavy quarks in an octet state go into a heavy quark in a singlet state. And since we need 2 of these interactions, this gives you 2 factors of R, the distance between the heavy quarks, which would give you this dependence here. And the non-perturbative correlator of the gluons gives you just a constant, and so on. And you can go even at higher orders in the multiple expansion, and you would get higher powers of R square. So what this is telling you is that parameterization for the static potential is given by this sort of formula, where you have these non-perturbative constants, which in principle are not known, but at least you know the dependence on the distance. So in fact, you can fit the short distance lattice data to this sort of formula, and you would see that you get a good approximation, a good description of the lattice data. And in fact, you can use this sort of fit to obtain the values of these constants. So we want to apply the same expansion for the spin-dependent, or the potentials of the spin-dependent operators. And in this case, at leading order, we get this come from this sort of Wilson loop with insertion of P, and this means that expanding the multiple expansion here, you get that we need an interaction between the heavy quarks with the gluonic state already at leading order. So this is these coefficients here coming from this gluonic correlator here. Then going further in the multiple expansion, you would get insertions of dipolar couplings, and this would give you again this R square dependence, while the non-perturbative gluon correlators are summarized in this constant here. So once we have this parameterization of the potentials, what we can do is compute the hyperfine splittings for quarkonium hybrids in terms of these constants. And then these constants can be determined by comparing with lattice results or lattice determinations of the spectrum of quarkonium hybrids. In particular, we did this with the results for charmonium hybrids obtained by the Hadron spectrum collaboration. So here we organize the different, so various states which belong to the same spin symmetry multiplet. So these are the quantum numbers of the hybrid states that belong to a particular multiplet. And then for each one of these states, you have the purple boxes, which correspond to the masses and uncertainties computed on the lattice. And then in blue, this is our results by fitting the non-perturbative constants to the lattice determinations. And here what you can see is that we can reproduce these lattice determinations, and this is all done keeping all these coefficients of natural size. So there is no contradiction within the EFT approach and these lattice results. So once you have determined these non-perturbative constants here, what one can do is apply the same computation to the Qualconium hybrid sector. And again, these are the results here. These are again Qualconium hybrid states grouped in terms of spin symmetry multiplets. And what is nice of these results, which again are these blue boxes, which the central line is the central value and the height of the box corresponds to uncertainty. So what was nice is that later on, the hadron spectrum collaboration also computed the spectrum of Qualconium states, in particular Qualconium hybrid states. And these are these results that are as on purple here. And the later results from the lattice agree very nicely with our predictions for the Qualconium hybrid hyperfine splitting. So we were very happy with these results. And well, the next thing I want to discuss is a bit different. And here I want to talk about these hybrid to standard Qualconium transitions. And here the idea is that so far I've been just discussing the results for the spectrum of these exotic states. However, to check experimentally these results, it is difficult because experimentally there are only easily accessible a few quantum numbers for the exotic states. So this means that predictions, for example, for these hyperfine splittings are difficult to check experimentally. But on the other hand, we always have information on the decay channels of the exotic states, and in particular, we know the information on the discovery channel, right? And in many of these cases, these decay channels are decays into a standard Qualconium plus some light quark mesons. And for example, I show you these two figures from the Bell collaboration, from this paper from the Bell collaboration, where you can see the cross sections to upsilon 1s, pi plus pi minus, and upsilon 2s, pi plus pi minus. And here, these three different peaks correspond to these three neutral Qualconium exotic states that I was discussing before. So the first peak corresponds to the upsilon 10,753. Then the second peak is the upsilon 10,860. And the last peak is the upsilon 11,020. And as I discussed before, the first and the last one, they fit very nicely into our predictions for Qualconium hybrids. So the idea was to study the transitions of these two states into standard Qualconium under the assumption that these are hybrid Qualconium states. And for this, we use the effective field theory formalism that I had been discussing, and also will work in the short distance approximation, which we hope it's a good approximation for Qualconium states. So here the idea is that these transitions will be generated by singlet to octet operators. So operators that change the heavy quarks going from a singlet state to an octet state. And the leading order operator here is the dipolar chromoelectric coupling, which is this one here. So the hybrid states, well, then you sandwich this operator between the hybrid states and the singlet plus some light quark meson states. So the hybrid states are defined as before here by this expression. So the heavy quarks in an octet state and a glue operator, which is the SP field. And the singlet or the standard Qualconium states are just generated by the singlet field. So we can compute this matrix element or factorize it. And this is what we obtain. There is the normalization factor that can be obtained through relating it to the gluon condensate. We have some light quark meson matrix element and some heavy quark matrix element. So this heavy quark matrix element can be computed because we know the wave functions from solving the Schrodinger equations, both for the hybrids and the standard quarkonium. And this leads to some selection rules, which are given here. So for this operator, for example, the spin is the same for the initial hybrid bottomonium and the final. So the spin of the heavy quarks is equal for the initial hybrid bottomonium and the final standard bottomonium. So the selection rules applied to the two states we are interested in means that they can only decay into H sub b's and some like quark mesons, and the allowed like quark mesons must have the same quantum numbers as this glue operator, which is a pseudoscalar isospin 0. So this means pi 0, eta, eta primes, and other eta-like resonances. So for the first three cases, which we have worked out this matrix element, and this can be done using the axial anomaly and some mixing scheme for these three states. This is the one we used. And well, with this, everything here is determined. We can compute the transition widths for various transitions. And this is the results we obtain. And these go from the MEV range for the largest ones to the KEV range for the smaller ones. Here in parentheses, there are the uncertainties, which are labeled by the different sources of uncertainty. And the leading order, or the term, the uncertainty that dominates is the one coming from using the multiple expansion. Then we can do the same sort of thing with the next two leading orders singlet to octet operator. This is in the heavy quark matrix expansion. And this is an operator that depends on the spin of the heavy quarks. And again, we can sandwich this with the initial hybrid and the final standard quarkonium plus light quark mesons. And this factorizes as before. From the heavy quark matrix element, we get some selection rules, which for these two states means that they can only decay, at least through this operator, to upsilon 3s1 or 3d1. And the allowed light quark mesons in the final states must be like scalar, isospin 0, so pairs of baryons, kaons, or etas, or also F0 resonances. And here we computed the first two cases in which this matrix element can be determined from a dispersive representation. So here the idea is that one takes this matrix element and decomposes it into an S and a D wave piece. For each piece, one defines a form factor, and the form factor can then be reconstructed from the imaginary part. So the imaginary parts are obtained from Watson's theorem, and assuming that the only source of imaginary part is the 2 pion and 2 kaon rescattering. So the reconstruction of these functions from the imaginary part is the Muschielis-Billy-Omnes problem, which is telling you that if you know the imaginary part and with these two extra assumptions on the analytical structure of the form factor, the general form of the form factor is given by this expression here. So this is the form factors. These are some omnes functions, which depend only on these 2 pion and 2 kaon scattering, and some subtraction polynomials that depend on the full process. And then this factor here is just a numerical factor depending on the isospin projections. So the omnes functions are the solution of this singular integral equation, where one needs to plug in information onto the pion and kaon scattering that goes into this T matrix. And for this, one uses a parametrization of these scatterings, of the experimental data of these scatterings. So this figure here corresponds to the phase shift of pi pi, and this corresponds to the partial wave of pi pi to kk. So these dots are experimental data, and then there are some parametrizations of this data which can be found in these papers. And taking these parametrizations and plugging them in here, one can solve for these omnes functions using some numerical techniques, which are in these papers. So the results we obtained for these omnes functions are given here. The first line is for the S wave, and the second line is for the D wave. Then the subtraction polynomials are obtained by taking the expression here and expanding it for a small s. So s is the square of the sum of the outgoing momenta of the pions or kaons. So one can expand this for a small s, and then require that for a small s, this matches a chiral representation of the form factor. So this kind of representation depends on some low energy constants, in particular 3 low energy constants, and this can be determined up to some uncertainty from the scale anomaly in the Feynman-Hellman theorem. And there is one free energy constant left, which can be determined from 2 pion quarkonium transitions, where a similar matrix element to this one also appears there. And with this, we also have everything determined, and one can compute, for example, these differential widths for the transitions. So these are the normalized differential widths. This X here is a rescaling of S. So we can plot all the differential widths from 0 to 1. Well, we computed transitions up to epsilon 1s, 2s, and 3s, and 2 pions for the 2 states we're interested, and also to 2 counts, but in this case only to epsilon 1s, since epsilon 2s is not kinematically allowed. So you can see there is some nice structure that hopefully can be compared with experiment. Then we have these total widths for these transitions, again, with the uncertainties in parentheses, with the label here telling you what are the origins of these uncertainties. And in this case, we have some experimental values for these. These are still very rough measurements for these widths, and can only be, well, they should be understood as ranges and not 1 sigma intervals. But already for this transition here, we find some promising agreement with our result. And finally, there is one extra possible computation, which is the computation of semi-inclusive widths for some of these transitions. And here the idea is that when the mass difference between the initial exotic and the final standard Qualconium state is large enough, then this gluon emitted by the heavy quarks going from an octet to a singlet state is energetic enough, then one can treat it in perturbation theory. And then this allows to the computation of the width as the, well, as the expected value of the imaginary part of this diagram here. And well, there are only these 4 transitions in which this can be done. And these are the results we obtained. And here, what is interesting is that if one adds these inclusive widths for the 11,020 states, for which we have a leading order 1 and 2 next to leading order ones, the result we obtain is this 28.4 MeV, which is compatible. Well, it's actually pretty close and compatible considering with uncertainties with experimental total width of the epsilon 11,020. So with this, reinforces our impression that this state here is a very good candidate to be a bottom-volume hybrid. And with this, I arrived to a summary. So I show you that the standard Qualconium spectrum has been well understood using effective theories for QCD. And I show you the recent developments in which I have been involved in extending these sort of EFTs to describe doubly heavy hadrons. I show you the results for Qualconium hybrids. We also have results for doubly heavy baryons, which can be found in these papers that I have not discussed. And for the future, we are looking for development of string models to evaluate these Wilson loops in the long distance regime. We also want to incorporate the mixing with the heavy meson thresholds. Also interested in looking into this new TCC++ tetraquark that has been recently discovered by HCB. And of course, if more input from the lattice is available, we can get more and better predictions using this effective field theory framework. So this is all. Thank you. And if you have any more questions, I'm happy to answer.
Thank you. Okay, thank you very much for a very nice talk. I will stop the recording.